Okay, so if you figured it out, the counting seems erratic, right? In fact, if you push the button really slowly, it really gets erratic. So here's what's going on. When you press that button, the contacts come together, and on a microscopic level, the contacts actually smack against each other, and then they literally bounce off of each other. These contacts can bounce several times, depending on how you push the button and the condition of the button. This microprocessor clock is actually very slow compared to many. I mean, my El Cheapo laptop microprocessor is running at 1.8 gigahertz, 1.8 billion clock cycles per second. That's 112 times faster than our PIC is running. Yet, the PIC is so unbelievably fast, it can literally count the microscopic bounces in your push button. So if your binary count appeared to go up by only 1 when you press the button, there's actually a very good chance that it actually counted to 17. It literally wrapped the count around, back to 0, and counted 1 number past where you left off when you pushed the button. That's how fast your program is being run. So this is a major problem you will have to deal with in microprocessors. Now there's a few ways you can deal with it with your program. And a common one is a series of steps. It reads that you've pushed the button. It counts that you've pushed the button, and then goes back and checks again. If the button is still pushed or closed, it adds to the count. If the button is now showing released because it bounced, it sets the count to 0 and goes back and checks again to see if you pushed the button. You have, so it starts counting again. But it bounces again, and so sets the count to 0, and starts counting again when it detects you've pushed the button. Now it'll wait until it's gone back for, say, 50 cycles in a row, where you were holding the button down. And then it counts that as 1 button press. Then it waits for you to release the button. But as you're releasing the button, the contacts can make and break multiple times as well. So it keeps count and does not consider you have released the button until it counts 50 cycles in a row where the button is released. Now, it may seem ridiculous, but this just gives you an idea of how fast and powerful even low-end microprocessors are. This process is called debouncing. And yes, your desktop computer scans your keyboard a bazillion times a second, not just to see what you pressed, but how long it stayed pressed. You can also do some debouncing with hardware. A capacitor across the push button, for instance. It takes time to charge up. In theory, it takes longer to charge up than it does than the time it takes for the bouncing to stop. So we're now going to modify our push button binary counter and throw in some loops and count how many cycles the button is pressed. And then do the same for the button release. Now we're going to cheat a little bit just to keep things simpler for this lesson. And we're simply going to count up 50 times where the button was red and showing as high. We won't reset the count to 0 in the middle of counting if we detect that the button, was released from a bounce, for instance. We'll simply count up to 50 highs red on the button, and we will call that a single button press. This is simply assuming that 50 cycles will take more time to perform than it takes for the bouncing to stop. You're also going to get introduced to the RAM inside the processor that you can use for your programs. You've got 16 bytes that are easily accessible, and they are located at memory address hex 0070. Now it's actually a 12-bit address, so the top 4 bits aren't used. There's no circuitry there, so it doesn't matter what you put there. And you'll notice the data sheet where they write the address sometimes as X070. The X just means it doesn't matter because it's not valid. So let's take a look at our code. Everything in the setup is exactly the same as it was before. We set up port C as outputs and port A as inputs. Whoops. And we start our main loop by checking to see if the button is pressed. When the button is pressed, we get sent to the button press loop. Now this is where it gets fun. Because this is still a binary counter, the first thing we do is we increment the number on port C, then we check to make sure it hasn't hit 16 yet, and if it has, we set the count back to 0, just like before. We then load up the W register with a number of 50. Now you can play around with this number if you want. This is the number of cycles the processor has to visit and count the push button input as a high before it lets the program proceed. We then take that number and move the comments of the W register to the file at hex address 0070. That's our general purpose RAM memory. You'll notice I didn't have to select the bank before I stored that number in the general purpose memory. There are a few registers in the PIC which are addressed in every single bank, and these general purpose RAM locations are some of them. Now here in the data sheet, we see that they hold the bottom bytes in every single bank. There's a bunch of reasons they did it this way, but for now, just go with the flow. Once we've got our numbers stored in the RAM, we then go to this loop of checking to make sure that the button is still pressed. Every time the program goes through the loop, it decrements the number and register address 0070. It counts down one number at a time. But this command also doesn't just decrement the number in the register, it also does a quick check. If the register is 0, it skips the next command. So this whole line is decrement file, skip the next command if 0. Now there are a few commands like this one with a useful feature. It's already a powerful multiple step command. Not only does it subtract one from whatever register I tell it to, it also checks that register to see if it's gotten to 0 yet. And you see this comma and a 1 after it? I have two options there. If I put a 0 there, it takes the number out of the register I told it to, it subtracts 1, and then puts the number into the working register. I can then continue to do some more math processing on it if I like. Or if I put a 1 in there like I did, it just stuffs the resulting number right back into the very register from which it came. So this is a very powerful command, and there's a few like it that we'll visit as we go along here. You can see them all in the instruction set you downloaded or in the PIC datasheet under the instruction set pages. So if the program has cycled through and has counted 50 times where the button was pushed when it visited, it now skips this next line, the go to count 1 command. It now reloads our general purpose RAM memory with the decimal number of 50 again. It now sits in this loop, waiting for us to release the button. If the button is pressed, it skips this next command, which is the command to count down 1 in our memory. It won't count down, it'll skip to the go to count 2 command, jump to count 2, and keep looping, checking to see that you've released the button. Every time it counts the button released, it subtracts 1 from the number in memory until it hits 0. When it hits 0, the instruction is to skip the next instruction, which is go to count 2. It skips over that instruction and sees the return command. It now returns back up to the call command where it left off and starts looping again, looking for that first time you press the button again. Okay, I hope that wasn't too confusing. The circuit is already built. You just need to flash your PIC with this new program. Away you go. See how it performs. You can change the number of counts as you like and see how it performs. Especially if you push the button slowly, that's the time when you get the most, making and breaking of the contact in the switch.